So today we're going to look at the last lesson in this unit on exponential and logarithmic functions, and we're going to look at a couple examples of applications of logarithmic functions. It turns out logarithmic functions are very useful when we apply them to number values that have very large range. So very large numbers of what we might say orders of magnitude. So let's take a look here. The three examples we're going to look at is using logarithms to describe or even solve problems around sound, earthquakes, and pH. So a couple things here from physics and chemistry and geology. All right, first let's talk about earthquakes. So often when an earthquake occurs, you hear them report on what the value was, or the strength of the earthquake. And the number that's reported is based on something called the Richter scale. And it's a measure of the strength or intensity of an earthquake. Now, each increase of 1 on the Richter scale represents 10 times the increase in the movement of the Earth. So the Richter scale number is really the exponent, right? Raising something or raising 10 to the first power means a 10 times increase, or a 30 times increase in the amount of energy that's released. Okay. So let's look at the Richter scale here, right? It can range from 0 to 10. And if we look at the top portion of the screen here, I'm going to put down what the amount of movement would be, right? So we get this range of values that goes from 1 to, what would that be, 10 billion. So the difference between something that's close to 0 on the Richter scale, maybe just detectable by instrumentation, but not felt by humans, compared to a 10.0 earthquake, would be 10 billion times more movement of the Earth. Okay, I don't think we want to be around when we have a earthquake with a 10.0 on the Richter scale. And then down below, we can do the same thing for the amount of energy, but instead of 10 being raised by the Richter scale value, it's 30 being raised by that power. So we get even a larger range of numbers between 0 and 10 on the Richter scale that represent the amount of energy released during that earthquake. So here's the key, right? The exponents used in the Richter scale are really referred to as a logarithmic scale. Remember, when we take the logarithm of something, we're finding the exponent. So each increase in 1 unit on the Richter scale is 10 times the increase in motion, or 30 times the increase in energy. So here are just some examples of what it might feel like for different Richter scale values. So up to about 2, typically these are not things that we can detect as humans, but instrumentation can detect them. And then from 2 to 4, generally we can maybe feel these things or see a lamp swinging, but no damage or great trauma from these earthquakes. But then we start to get above 4, and we start to see some small objects falling or breaking. Up to 6, furniture starts to move. We may get cracks in the walls, maybe even glass break. And then above 6 is where we start to see significant damage to structures. So even well-built structures here in California, right, where we've been building homes and buildings to survive earthquakes for quite a few years now, above 6.0, you'll still see some damage to that. Above 7, you'll see entire buildings that are shaken off of their foundations. You might see large cracks open up in the earth. Underground utilities like pipes and drainage pipes broken. And then above 8.0, most all structures will have significant or even catastrophic damage. And above 9.0, pretty much anything man-made is going to not survive that. So fortunately in California, right, most of the earthquakes that we have are small ones. It's better to have a number of small earthquakes that continually release the pressure building up along the fault lines than it is to have one large. But occasionally we do have a large earthquake in California, and eventually we will once again have a large earthquake in California. So here are some examples of those earthquakes. Right here in Santa Rosa, the last big earthquake we had on the Rogers Creek Fault, which travels pretty much right through downtown Santa Rosa, was a 5.7. That was back in 1969, and quite a few of the older brick buildings in downtown Santa Rosa were destroyed in that earthquake. You can see San Fernando earthquake in the early 70s was fairly large. And again, a lot of buildings back in the 70s had not been retrofitted or built to earthquake standards, so they had widespread damage. Really, it was in that San Fernando earthquake that most of the changes to how we build things in California came into being. Northridge earthquake, another large one. Right here in the Bay Area, 1989, maybe just a little bit before you guys were born. 7.1 in Loma Prieta, they called it, down near Santa Cruz, but widespread damage in the Bay Area. We had bridges collapse, freeways collapse, quite a few people died in that earthquake. And then one that you may remember, the earthquake at 9.0 off the coast of Japan that created a huge tsunami wave that swept in and just destroyed many cities along the coast, and many people injured or lost their lives in that. So how do we compare the strength of any two earthquakes along the Richter scale? So let's take a look at the 2011 earthquake in Japan and the 1969 earthquake in Santa Rosa. So let's first compare how much stronger was the movement of the Japanese earthquake. So we want to just take their ratio, right? Starting with the Richter scales. So 9.0 in Japan divided by a 5.7 in Santa Rosa. Now, remember the movement is 10 times greater for each increase of 1 in the Richter scale. So we want to rewrite this so that our 9.0 becomes the exponent, and the same thing with 5.7. So here's what the actual movement difference would be. In Japan, 10 to the 9th compared to 10 to the 5.7. So grab a calculator, right? First, though, we can apply our property of exponents where we subtract, right, the exponent in the denominator from the exponent in the numerator. So we wind up with a ratio here of 10 raised to the 3.3 power. So grab your calculator now, punch that in, and we see almost 2,000 times greater movement in the Earth in the Japan earthquake of a 9.0 than what we felt here in Santa Rosa. So even though we had a significant amount of damage in Santa Rosa with a 5.7, you can understand that huge damage, right? If we had a 9.0 here in Santa Rosa, there's not many buildings that would be able to withstand that. How about the energy that was released in the earthquake? So same thing, except now, right, instead of 10 raised to the Richter scale value, we're going to take 30 and raise it to the Richter scale value. So same thing, right? We'll subtract the exponents, but now it becomes 30 raised to the 3.3 power. And the amount of energy from that earthquake was 75,000 times greater than that in Santa Rosa. Okay, so understanding that the Richter scale is a logarithmic scale that's using the exponents of movement or energy allows us to make comparisons here between two different earthquakes. All right, let's move on to another example here. This one is from physics, and it has to do with how we measure the loudness, or sometimes called sound pressure level of sound. And it's, again, a logarithmic scale. And it compares what we call the power intensity variation of a particular sound to the threshold of human hearing. Now, you probably heard this term before, right? dB or decibel, and that is named after Alexander Graham Bell, who did lots of work around sound and recording devices, and the telephone sometimes is credited with the invention of the telephone. But we use decibels to describe how loud a sound is. So here's what the equation looks like. And you can see we use a logarithm to do this. So common log base 10 we take 10 times the common log, and then it's the ratio of the two measured power intensity levels. So the measured level is on the top, the reference level is on the denominator, and the reference level is just loud enough that we can detect it by human hearing or human ears. But what this results in is that each 10 dB increase is 10 times the increase in the sound pressure level. Now, what is this reference level? If you could hear a mosquito about 10 feet away from your ear in a quiet room, that's kind of the lowest sound level that the human ear is capable of detecting. So that's, think of that as our reference level here when we're calculating sound level of other sounds compared to that. All right, so here's a scale with some examples. At the very bottom, you'll see the hearing threshold, and it actually shows the sound intensity level, right? It's very small, 1 times 10 to the negative 12th, but that corresponds to our 0 dB level, okay? Because think about it, if you take a ratio of two numbers that are the same down below, in other words, I measured is the same as I reference, then the common log of 1 would be equal to 0, right? Anything raised to the 0 power gives us 1. So that's our mosquito buzzing. Let's go up the ladder. Normal speech, just in a room, would be about 60 dB, or in other words, 6 times louder, or 60 times the sound pressure level. Busy traffic on the streets. If you stand out by the airport and watch jet airplanes take off, that sound can be as high as 140 dB. And anything above about 100 dB is considered unhealthy, especially if it's for extended periods of time. You can begin to experience pain and actually at least temporary loss of hearing. The loudest sound that can be produced is something we call a sonic boom or shock wave. So this is what occurs when an airplane flies faster than the speed of sound and creates a pressure wave that can be as high as 200 decibels in sound. And it sounds something like this. Now, when I was growing up, it was pretty common to hear sonic booms as military aircraft would fly over at high speeds. Nowadays, it's illegal to create sonic booms, at least over populated areas. But if you went out in the Nevada desert, where the military does a lot of training and flying, you would still hear sonic booms being generated out there. All right, so let's look at an example. We want to find the loudness in decibels of a police siren with a sound intensity level of 2.2 times 10 to the negative 5th watts per meter squared. Okay, so we're going to use our formula. Remember, the reference level is 1.0 times 10 to the negative 12. So we're going to put that in at the bottom as our reference level, and then the 2.2 times 10 to the negative 5th as our measured level. And then the rest is really calculator work, right? We take the ratio of these two values in scientific notation. We get 2.2 times 10 to the 7th, and then take the common log of that and multiply it by 10, and we see that the police siren going by would have a sound level of about 73 decibels. Okay, so there's an example of how logarithms are used to create a loudness scale for sound. All right, the last example we're going to look at is pH. So again, if you've taken chemistry, you talk about the pH of a solution or material. It has to do with how acidic or basic a solution is, with 0 being extremely acidic. Things like hydrochloric acid, those types of acids are going to be having a very low pH number. 7 would be considered neutral, and then base or basic solutions would be as high as 14. Now again, if you look at the numbers here, They are based on what they call the hydrogen activity level. Okay, so I believe it has something to do with the amount of free hydrogen uh, uh, electrons or atoms that are available in the solution. So that activation level, that hydrogen activation level, can vary from 1 to 1 times 10 to the negative 14th. If you look at the bottom, you see all those zeros. There'd be 13 zeros there than the 1. So again, a logarithmic scale is very useful for us working with such a large range in our number values, right? This would be an order of magnitude of 14, from 0 to 14. So if you look at the right-hand equation here, pH is calculated by taking the log of 1 over the hydrogen activation level. So let's look at an example of how we would apply this. So let's say for a pH solution, it has a hydrogen activity level of 2.4 times 10 to the negative 6. So we're going to plug that in to our formula, and we start with it in the denominator. And then let's grab a calculator, right? And if we take 1 divided by 2.4 times 10 to the negative 6, we get 416,667. And now we take the common log of that. So in other words, 10 to what power would give us 416,000. And if we do that, we get 5.6. So this would be a solution that is slightly acidic, right? 7.0 is neutral, and 1 would be very acidic. So it is on the acid side of the pH scale. Let's do one more. And in this case, I'm giving you the pH value and asking you to find the hydrogen activity level. So we'll plug in 3.4 for pH, and now we want to take log of 1 over x. And what would x be in order for the logarithm of that value to give us 3.4? Well, how are we going to solve this? It's a logarithmic equation, right? And we want to rewrite it in exponential form. So let's do that. It would be 10, because we're common log, raised to the 3.4 power equals 1 over x. So let's do a little algebra here to solve for x, right? We want to get x out of the denominator, so we'll multiply both sides by x, and then divide both sides by 10 raised to the 3.4 power, and we get this number. And then on our calculator, we could go ahead and say, what is 1 divided by 10 to the 3.4? And we get 3.98 times 10 to the negative 4th. So that would be our hydrogen activation or activity level. All right, so a couple examples there of how we can apply logarithms and work when we work with the pH scale. All right, so that's it. We've looked at earthquakes, sound, and pH problems.